Okay, Assalamualaikum warahmatullahi wabarakatuh. So last Thursday, we did stop at the resistive and inductive load with freewheeling diode, and we have the back EMF at the output to look into the analysis of if you have the DC motor as the load for your control rectifier. So we have single phase control rectifier, and at the output we have this DC motor, and we use the freewheeling diode to remove the negative area. Remember, we have this negative area. Okay, so we want to remove that negative area, and therefore we use the freewheeling diode, right? And before we proceed to the next topic, which is on the effect of line source inductance on current commutation for single phase full wave control rectifier, I would like to go back to the one of the example that I've shared with you through the Padlet, but let's have a look together on the final exam. This is a last semester final exam questions, right? The July 2023, and it is under question 2, and this is more questions on the control rectifier with the R plus L conditions. And so the question asks the first part A, actually to explain the extension angle beta for a single phase half wave control rectifier with an RL load, and then draw the circuit diagram of the rectifier and the required voltage waveforms to support the explanation. So you need to explain what is beta here, why we have beta in the circuit in the case of R plus L as the load. So as the solutions, you can see that the extension is simple. The extension angle beta defined as the angle at which the current returns to zero, as in the case of the uncontrolled rectifier. So very much similar to the uncontrolled rectifier, whereby where you can see that the current, the input current, goes to zero, isn't it? Goes to zero, and at that particular the extinction of the current, then we have beta at that point. So if you look at the note, the equation can be obtained as this: I theta. This is also theta, right? Omega t is also a theta. How to write that? So V peak. Sometimes you have this is the solution actually prepared by Dr. Azlan. So he used a VM instead of V peak. So if I make the solution, we put that Vs with a peak, which is the amplitude of the supply voltage, divided by Z. Z is the load impedance, and then we sine omega omega t. I think that is this is phi, not this is phi, not theta here. Okay, phi is the load angle inverse tangent minus 1 omega L over R, isn't it? Right? And then we have this sine alpha minus phi again. So this is phi, this is phi, and this is theta, this is theta, and we have plus here because the equations from alpha to minus theta. If we refer to the my monograph, it is phi minus alpha. This is similar equation, and here we have alpha minus theta again, and we have the what we call this a tau, isn't it? The tau is the time constant. So time constant, tau equals to L over R. This is similar, the same equation. You can write the equation from the monograph, no worries. You can be accept. So which must be solved numerically for beta. So to get the beta, if you still remember, so if you look at the current, so we have a positive cycle rate. This is a supply voltage. So if you look at the current, we do like this. Sorry, it will rise and then we reach the maximum and then come back equals to 0 at some point, isn't it? So this is call it alpha, for example, and this is your beta, isn't it? Okay. All right. So this is equation. This is equation to describe that current equation, and if we set alpha equals to at beta, then this is equals to 0. All this current equals to 0. So um, this is for half wave rectifier, but it can be used for the full wave rectifier as well, right? So this is the waveform, the circuit diagram, and then this is the voltage and current as I just drawn just now, sketched just now, and that's it for question part A. And then let's have a look at part B, whereby you are given this case where now we extend to the question goes to the single phase full wave rectifier driving an R plus L at the output. Okay, so figure 2b depicts a controlled full wave bridge rectifier assuming a 45-degree firing angle and highly inductive load. So first we consider we have the highly inductive load conditions. This is a highly inductive load condition, so we just assume we have a IDC, so which means you can ignore that, and then you replace a constant current at the output because that is the first situation, right? So you have a constant current IDC. So sketch the waveform of Vs, IAC, the input current, VDC, and IDC. Remember, we have 45-degree firing angle, the rest. So let's have a look at the answers. So that is your question 2b. Okay, because we have a constant current at the output, therefore the circuit falls under continuous current mode, isn't it? We have two conditions, discontinuous and continuous current mode or situation, isn't it? So in this case, if you refer to the node, then we have this output voltage because at the beginning, the current flowing in the circuit forcing the thyristor 2 and thyristor 3 to thyristor 3 and thyristor 4 to turn on, and therefore you have this output voltage copy or the negative of that voltage here, and then we have, and then you trigger thyristor 1 and thyristor 2 at that point, then you have this output voltage again, then it continue to till negative area, and then you trigger again. This is where you trigger thyristor 3 and thyristor 4. Okay, so that's the output voltage. Because we have a, you don't have to worry on the continuous or discontinuous, because it's mentioned that firstly we consider a highly inductive load, so we have a constant current at the output. Okay, so that's why we have this waveform. Okay, right, so next is to draw IAC and IDC. So it's a constant current, so this is the output current, constant ideal IDC current, and at the input side we have a square waveform. Okay, square current waveform, and it shifted with a value of alpha here, isn't it? Shifted to the right with the value of alpha, the firing angle to your thyristor 1 and thyristor 2. Okay, so that is the number 1. And then part number 2, derive the expression for the average output voltage. And again, you can use the you can refer to the node, so you just simply you integrate from alpha to alpha plus pi, and then you have this pi because it repeat by pi. Okay, and that's why you have that, and then you can simply use the trigonometric function identities, and finally you find out that the output voltage is defined by this equation 2 Vp. Again, if I do the solution, I will give this the notation for the peak value with a hat there. So you have pi cos alpha, right? So that is the output voltage, so you get full mark for that. And then next you have to read the question carefully. Okay, it says if the rectifier in question 2b has an L of 20 millihenry. Now it consider the case of 20 millihenry. Instead of a highly inductive load, for the first case here, now it replace, or it mentioned that we know the value of L, and the L is equals to 20 millihenry. So determine the extinction angle. So you need to find what is beta. RMS load current. So you need to do the root mean square. Remember, I load is IDC. The RMS. Okay, so that will be equals to root mean is 1 over T. You integrate through to T. The current, the output current IDCT dt, you squared the current, isn't it? So that is the general equation. Okay, so you need to get the RMS load current, average output voltage, and power absorbed by the load. Okay, so here again we can use the current equation from the uncontrolled for the full wave, for the half wave that we just written here, isn't it? This is a half wave, so we can use that equation to determine beta, right? So you have that equation again. Come back to the solution. So this is your equation just now. Dr. Azlan used the SMath, if I'm not mistaken, right, to solve this. If I do the solution, I will use the MathCAD, as I shared with you before. Okay, so you define the, you look at the how Dr. Azlan prepared the solution. It defined all this value. 230 volt is RMS, R equals to 30 ohm, and then we have L equals to 20 millihenry, and all the degree RMS, and we have tau, the load angle, the time constant L over R. Then the rest Z is calculated here, and here Dr. Azlan used a theta instead of a phi. Okay, so my notes I put is a phi inverse tangent omega L over R, and then here is alpha, so you convert into radian, 0.785. Right, so now we have V omega T Vm peak sine omega T, and then you define this equation, and then SMath use this function here. Okay, set it to 0, and then you want to calculate for beta, so you set beta here, and you have to tell what is a beta value, the initial condition. Remember when you use a calculator before, we need to define the initial conditions of beta, so you put pi there, and this is the range of 2 pi, the range of beta. Okay, so this is defined by the SMath software, as which the Azlan use. Okay, so beta equals to 3.348. Okay, but for you, you need to use the calculator, isn't it? Set the calculator, and then you calculate for beta, and you get the 3.348. And since this beta is lower than alpha plus phi, isn't it? Alpha plus pi, isn't it? So this is a discontinuous output current condition. Okay, so therefore you need to use the you can either use the equation from the notes, or you can simply integrate. If you use a calculator, you can also use you don't have to memorize all the equation, and you use a calculator to do that, alpha beta, that you get 174.59. Or else you need to use this is from the equation. From the notes, you have this equation. If you remember this, then just use it, but it's less. I mean, if you remember the equation, go ahead, use that, or if not, you just use a calculator, but write the actual general equation, alpha to beta and the rest, and you get that answer, that 174.59. And then look at this again, I out equals to root mean 1 over pi alpha to beta, and simply you get this answer. So you can use the calculator to do this as well. Okay, you can use the calculator to do this as well, because we know the equation here. This is your equation, and then you put that equation, you square, then you get that answers here. Okay, right? So but you have to be careful while you need practice. Okay, you need to practice, try a lot, because by using calculator you need to put all this equation here inside that, and then you have to square, do it carefully, and finally you get this is 7.041 ampere. And finally, to get the output power, remember when you have R plus L condition, always to get the output power, you always need to look at the IRMS. Okay, IRMS of that current, and then squared, and then you get the to get the what we call it, the power, the power for your output. Okay, right. So next, that's it. Okay, so I hope you understand how to solve this. There's a solution just for you to understand. Look carefully at this. Okay, so now let's continue with the notes. We go into the effect of line source inductance on current commutation for single phase full wave control rectifier. So we go back to the highly inductive load condition. You have a full wave rectifier, and then we have this what we call it sorry, at the output we replace R plus L, because it's a highly inductive load, we replace with a constant current I DC here. Okay, and we have LS. This is actually come from the transformer winding, from the cable, so it appears as the source inductance. Right, so I put that, and it just actually, if you understand the uncontrolled version of single phase full wave control rectifier, so you just simply extend this when you delay the turning on of your thyristor. Okay? If the diode happens right at the beginning, for the control rectifier you just shift to alpha here. So instead of we have this at a 0 second or 0 radian, now we have alpha degree or alpha radian. Okay, so it shifted to the right, so you have this current waveform. So the explanation is very similar to what we had before. So during the overlap, okay, due to the source inductance here, there is an overlap of current to transfer from thyristor 1 to thyristor 3, or vice versa from thyristor 3 to thyristor 1, isn't it? So here we consider at the beginning. So if you look at the beginning, so it's this transfer of current from IT3 to IT1. So we wait until thyristor 1 and thyristor 2 to be triggered. So here we have thyristor 1 and thyristor 2 triggered at alpha. Then the current start to rise, and the current for thyristor 3 and thyristor 4 start to reduce. This is the 3 and 4. So the current start to reduce, so there is an overlap. So during this overlap of current, we know that all thyristors are on. So this is on, this is on, all thyristors on. So therefore it appears as a short circuit, and if you measure the output voltage, you see a 0 voltage short circuit. So you have 0 voltage. So that's why during the overlap period, okay, in commutation interval, there's two names. One is the overlap period, the other one is interval, commutation interval. They're all the same respect to that overlapping of current. Okay, so during that time you have a 0 voltage across your output. Okay, so this is the output. Then now you need to first to identify or to determine what is mu angle. You need to look at what is a mu angle. So remember, we are looking at the transfer of current from thyristor 3 to thyristor 1. So after this overlap, so if you look closely, after the overlap, the current that flow is the IT1 through IT1. Okay, so let's look at the how it derived and look at the during overlap, the equivalent circuit becomes this. This is because actually there is a IU here. You have to what you call it, draw a current equation, current IU, the overlap current, and this current must follow the flow, the current after the overlap. So it will follow the thyristor 1 current. So you have a thyristor 1 current flowing here, thyristor 2 flowing here, thyristor 3 is flowing here. So it follow the thyristor 1. So you have to draw overlap current IU to follow this current thyristor 1. That's the 1 current. So draw that. So this is IU. Okay, then you do the KVL again. It's very similar what happens before. And now we have this alpha plus u, alpha plus u, and we have minus IDC. This is with respect to the input current. So when you look at the input current, this is your input current here. So your current start from minus IDC to IDC. Start from there, it end up at that point. So you have a minus IDC to IDC for the limit of the current equation. Okay, and solve that, it gives you this equation. So you have an extra minus alpha in your equations there. Minus alpha. So that is how to get the U. If you know what is the value of LS, IDC, and the rest, you can simply calculate for mu. Okay, so that is a mu. Okay, let's continue with the output voltage. So again, when you look at the voltage waveform here, so this is actually the same as we did before. We need to find the voltage drop, right? So the loss area here, voltage drop there, and then we look into the average of this voltage drop, and then simply we just we know that the output voltage, the average of the output voltage for a normal or without the source inductance a situation, we have this sort of a current waveform. Do it. We have this current waveform, right, straight without the, so you just minus the voltage drop here. Okay, so similar methods we're going to apply. We need to find this area voltage drop, the average of this voltage drop, and then we just simply minus subtract the output voltage equation, the average of the output voltage equation in the case of without the source inductance, minus this voltage drop. Okay, so that is what we're going to do. And if you look at this integration, of course it is from alpha, this is alpha to alpha plus mu of this voltage waveform, isn't it? Okay, so that's why we have this integration, alpha to alpha plus mu v peak sine theta, and if you solve that, you get this, and this is a similar equation. So you can equate this equation, and finally you find out that the area voltage drop, the voltage drop equals to 2 omega ls IDC, and if you want to find the average voltage drop, you have to divide by pi, and the average voltage drop is equals to 2 omega ls IDC. And if you take the equation and you use the equation for the without the source inductance version, and then you just simply subtract the voltage drop, isn't it, to get the total average drop for the case of source inductance. Okay, then therefore when we look at the equation, we see that there is a reduction in the average of the output voltage VDC, and The other thing is, when it comes to source inductors, there must be distortion on the voltage supply of the current of the converter at the point of common coupling. This is how we have that. So this is the supply voltage right from the supply, and then at the VPC point of common coupling, and this is inversion of that waveform. Okay, so if you look at the point of common coupling, it inverts this, right? So at this is the output side, isn't it? This is the output voltage, and if you refer to the point of common coupling, at the point of common coupling, whereby we measure that at this point. Okay, at this point, this is known as point of common coupling, whereby at this point we're going to connect to another load. Remember, I did explain that before. So this is, this point will be connected to load 2, sorry, load 2, and the other one load 3 and 4. So this is known as point of common coupling, PCC. Okay, so this PCC actually invert back whatever the voltage that you had you have in the output. So if you invert that, you're going to get that sort of voltage at the point of common coupling. So this voltage will be supplied to another load, other load in the system, load 2, load 3, load 4. So they'll be having a problem with the harmonic. That's all right. So that is the we call it the effect of having source inductance in the front end. And next we look into the inverter operations. Yes, even though this circuit is a rectifier, at certain amount of a certain value of alpha, you can see that, and in the case of a constant output current, we have the constant output current at the output. For example, as we mentioned before, we drive a DC motor, so we always have this armature current, which is a constant current. So when you at certain value of alpha, you can see that the output voltage is reverse. Okay, so here if you look at the output voltage, okay, for alpha equals to 60 degree, okay, this is your alpha equals to 60 degree, okay, and this is your alpha equals to that point is where we have alpha equals to 0 degree, and you have that delay, the firing angle of thyristor 1 and thyristor 2 with 60 degree. So if you measure the output voltage, we get the sort of 108 average voltage. Okay, still a positive, isn't it? So we have this positive negative polarity, and the current goes into, this is a constant current in the output. So therefore actually this become the load, isn't it? Because the current flows, so current flows through there, so the current flows into the positive of the output voltage. That means this is a load, right? So the transfer of power, the power flow is actually from AC to DC. And this is convention. You have to look back at the convention of the electrical circuit. So if the current flows through flow into a positive polarity, that becomes the load, right? So this is a load. Okay, however, if you extend that alpha equals to 120 degree, so you got to see that this blue waveform, which is the output voltage, is more negative now. So if you refer to that area is more negative to that area, isn't it? And if you measure that, the output voltage become minus 108 instead of positive. Now the polarity change to minus 108. So if you refer to this diagram here, you can see that the polarity change. We still have the same current flow. Okay, so now you see that the current actually leave from from the positive terminal. Three. Okay, it leaves from the positive terminal. That means the current now, this side become supply, and that become load. Okay, so these conditions actually mostly occur in the motor drive, electrical motor drive. So you can read the explanation here. So during the inverter mode operation for alpha greater than 90 degrees. So if you have the condition of alpha greater than 90 degree, the load energy can be fed back from the load circuit to the input AC source. So now if you look in terms of the quadrant, so this is actually the quadrant, 4 quadrant that describe the DC operation, right? The DC motor operation. Okay, so the first quadrant here, whereby you have this motoring, normally we put it a motoring region or quadrant, and this is braking. Okay, and then we have a negative motoring, can't remember, reverse motoring for a second, and this is reverse braking. Okay, so if you have that condition, the x-axis here is to represent the IDC, the positive, the y-axis represent the VDC. So we have a VDC is positive and negative, isn't it? So by varying the alpha, you can see that the alpha, the output voltage vary from positive VDC to negative VDC, but you still always have the constant positive current IDC. So that's why it operates in these two quadrants. So this is known as a two quadrant operation. So the full wave, you can read that. Okay, and that's actually for the single phase control, and also as the uncontrolled rectifier. Right, so now we start a bit on the three-phase uncontrolled rectifier. Just a little bit of the touch a little bit on the three-phase uncontrolled rectifier before we continue with the next class on Thursday. Okay, so three-phase uncontrolled rectifier. So as the name implies, we know that three-phase refers to the input side. Instead of only a single phase AC, now we have three-phase AC. So we have V red, V yellow, and V blue as the notations between the three. And if in terms of phasor diagram, you always draw like this. You have a V red with the angle of 0, and then you have V yellow, which is the angle of minus 120 degree, and we have another phase which is V blue, and the angle is minus 240 degree. Right, so that is the angle for each of the phase if you consider a Y connection. So we have a Y connected Y connections, or the we call it positive sequence as well. So positive sequence, we have V red, V yellow, and V blue. But if it's negative sequence, you have V red, V blue, V yellow. Right, so that is a negative sequence, but normally as a standard we use the positive sequence. Okay, right, so next let's look at the first. We have two circuit to discuss. One is known as half wave uncontrolled rectifier, and the other name is also known as a midpoint rectifier. Okay, midpoint or half wave. And the other circuit is known as full wave or full bridge rectifier. So we're going to analyze as what we did for single phase. We have half wave rectifier and full wave rectifier. That also applicable to a three phase. We have a half wave, or the other name for the half wave is a midpoint rectifier. and the other one is a full wave or full bridge rectifier. Uncontrolled because we still use the diode. If it's a controlled rectifier, then we're going to replace that with the thyristor. Okay, so we always start with a resistive load. I hope by now you know how to draw the three-phase supply voltage. This has been discussed during the very first class. At the beginning, I show you how the technique to draw the three-phase supply voltage, V red, V yellow, V blue. Okay, so we have what we need to do is draw the XY axis, and then we draw the dash, right, horizontal line there, and then we start to draw the the triangular waveform. So extend to the negative cycle, so you can start that right just like that. So extend to the negative cycles, and then do the same to this one. Okay, and then do it for 5 triangles. 1 2 3 4, another one. Okay, 5 triangles there, and then you connect the tip of the triangles. Okay, and that also extend to the negative, so you have that, and that as well. So now you have the bold this first. So you have V red, you can bold that, write a nice sinusoidal waveform there to connect all the lines there. Okay, so there's a V red, and then you can change to V yellow if you like. You can have this a V yellow. Right, and finally blue, isn't it? So you can change that to V blue. So we have V red, V yellow, and V blue waveform. Okay, I can do it again. Okay, so V red, V red, V yellow, V blue there. Okay, and here is we have this V blue. Okay, right. So this is a three-phase phase voltage. What we are drawing, I'm drawing now is actually the phase voltage. If you want to draw the line-to-line voltage, it will be different. Steps to do it. Okay, right. So now, so now we have what? This is known as a half-wave uncontrolled rectifier because we use the diode, and then it is connected as this is a three-phase supply, and then the anode of each of these diode will be connected to the positive polarity of your supply voltage. Okay, so this is anode, 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 and the anode of each diode there will be common. So that, and this point is known as a midpoint of the diodes, and that's why it is known as a midpoint converter. Then we connect to the first load, which is the resistive load, and you have a common ground. So you can also do this to connect that to that, right? So this is a common ground if you like. Yeah, so it's best if you want to draw like this. It is allowed to draw that. So you have one. So the current will flow at the output and come back to that. Right. So if you have a current, so the current will flow into that path. Okay. So now we have to diode 1, diode 2, and diode 3. How to determine which diode is on at anytime, at all, which diode is on at each of the seconds or at any time here. There must be a we call it a reference. Okay, so to determine which diode is on at any time. So here you can determine, you can identify which diode is on by applying these notes there. This condition. So at any instant, at any point, at any time, the diode, okay, the diode which its anode has the highest amount of instantaneous phase voltage will conduct. So this is the output voltage. Sorry, this is a supply voltage there. Red, yellow, blue. Okay, red, yellow, blue. At any instant, it says that at any instant, the diode with its anode at the highest voltage, at its any voltage phase, red, yellow, blue, and which phase that has the highest voltage will be turned on. So if you start with a 0 time at 0 second here, so if you look at the 0 seconds there, okay, so the most positive voltage is at VB, isn't it? At VB. So therefore, the diode, this is diode red, diode yellow, and this is diode blue. So you can see that this diode will operate first, and the rest will be turned off. Okay, so we have only this diode is on, because at the beginning the blue waveform is highest. So this diode will be on and the rest will be off. So this voltage will actually equals to VB. So the output voltage will actually follow the blue waveform there until the intersection between red and blue. Isn't it? So we have red and blue. Just after that intersection, we see that V red is at its highest potential, isn't it? So that in that region, diode red will turn on, and diode yellow will be off, diode blue will be off. So VDC will now jump to and equals to the red phase voltage. So it will follow the envelope of the output voltage. So now you follow the red phase voltage. The next, yellow phase voltage at its highest, so it will follow the output voltage will follow the yellow blue and then come back to blue. So the output voltage actually copy the or the envelopes. You only copy the output voltage waveform, supply voltage waveform, the envelope, the only that pulse. You can see the 3 pulse there to complete one cycle. So each pulse, so if I may have this line to set the border between that and that, that and that, so we know that this is the red, the yellow, this is the blue. Turn on. Great. So each of these diode will turn on for 120 degree. So this is also 120 degree. This is also 120 degree. Okay, so therefore, if you can, and the other thing is, the important thing is to look into what are the cross, what is this? Okay, so what is the angle from 0 here to the that angle? So if you do the can prove that using the equation. We know that VR, we can put it as a V peak phase, sine theta, and then you have V blue, isn't it? V blue equals to V peak, the same phase, sine theta minus 240 degree, if you like. Yeah, so you equate V red equals to V blue, and you can solve for. So now you can have sine theta equals to sine beta theta minus 240 volt degree, and you can find that this theta equals to 30 degree. Okay, so at theta equals 30 degree, you will see that the output voltage, no, the intersection between red and blue, voltage, and this alpha, this angle is pi over 6, which is 30 degree. So this is also known as a commutation angle. Commutation angle is also known as a commutation angle. So after 30 degree, the yellow phase, the current and the voltage, finally the instantaneous output voltage. So you can read that VDC equals to VP cos theta. And to solve this, what you can do is you can integrate. So this is the output voltage rate. So you integrate from, this is 30 degree, pi over 6, until what? This is 0. This is 30 degree. And then we know that the pulse is 120 degree. So this is actually 150 degree, which is 5 pi over 6, is that it? Yeah, 5 pi over 6. So you can integrate. Okay, you can integrate. You know that the output voltage V out equals to 1 over T, 0 to T, V out T dt, is it? So get the average, and you can change that to 120 degree is 30 is pi over 6. Pi over 6 multiplied by 4, isn't it? So 2 pi over 3. So here you have 2 pi over 3, and you integrate from pi over 6 to 5 pi over 6, and you can have V peak phase sine theta d theta. You can solve that, right? You can solve that, and you get the average equation. Or what you can do is you can take this one pulse, and just take one pulse here. Okay, just take one pulse, and then you shift to the left. So you shift to the left until the peak of that pulse is at 0 time here, at 0 degree or 0 radian. Okay, so you modify, you adjust so that you can have a 0 degree or 0 radian, and therefore at the positive side you have pi over 3, positive pi over 3, which is 60 degree, and at the negative side you have negative pi over 3, and you have negative 60 degree. So again, total will be 120 degrees, isn't it? 2 pi over 3. Okay, and in this case, now your equation now become V peak cos theta. V peak cos theta. So just now we have V peak sine theta, isn't it? But if you want to maintain the angle, the same area here, isn't it? But if you change and modify the peak at the 0 second or 0 radian or 0 degree, so you have that as a V peak cos theta. So this is cos waveform, isn't it? Fully as cos waveform. So that's why you have equation of V peak phase cos theta. So if you solve that, V peak cos theta, and this is the limit, right, from minus pi over 3. So if you solve that, you get the, look at that, minus 2 pi over 3, and you found out that the output voltage can be defined by this equation, 3 over 2 pi V peak line to line. Or you can maintain this equation, if you like, in terms of V phase, 3 root 3 V peak phase over 2 pi. So this is the average output voltage of a midpoint converter when the load is a purely resistive load. So I think that's it for the class. We just give an introduction and the basic circuit of half-wave uncontrolled rectifier, or what we call it as a midpoint converter. So we have another name, which is a midpoint converter. So we look into the operation. We know how which diode will be turned on at which time by applying this condition. Okay, so by applying and looking at this equation notes, we know that which diode will be turned on at any time. No worries. Okay, and finally you derive for the average output voltage. Okay, so we stop at this, and we're going to continue next stage, inshallah. Okay, thank you very much.